decided to model the feedback system for a driverless car. Every year, many accidents are caused by either reckless driving, drunk driving, or falling asleep at the wheel. And we believe that modeling this system could help reduce traffic and improve the safety of our roads, which would benefit society overall.
We decided to model velocity. Our controller will be used to reach and maintain a constant velocity. For our system, our dampening coefficient represents the dampening from the tires on the road, and that's specifically a dry road. Our dampening coefficient is 230 pound-seconds per foot. Our mass of the car, we're modeling our car as a Prius, is 3,010 pounds. The force is representing the force of the engine applied to the car, and our velocity is the velocity of the car, and our goal velocity will be 30 feet per second.
So for our basic block diagram of our system, right up here we have R of S as our input, Y of S as our output. Our plant, shown here in the dotted box, is modeled as G of S. When we come down here and look at our transfer function of that G of S, that comes out to be 1 over ms plus b.
So as you can see with our stability analysis, this is our transfer function. And as far as stability, you can see that we have one left-handed pull and no right-hand pulls. The system is biostable. And looking at the Nyquist plot, you can see it also that there's no encirclement of -1 plus j 0. That means n is 0, and because there's only one left-hand pull, p is 0. Z is p plus n, that's 0, so we do have a stable system.
So for our design specifications for our feedback system, we have a rise time of less than 5 seconds, a settling time of less than 20 seconds, a percent overshoot of less than 5%, a final value of 30, and a steady state error of 0. These translate over into having a crossover frequency, or our frequency on our Bode plot, being greater than 0.44 radians per second. With a 0 steady state error, we would need a gain margin that was infinite. And then our percent overshoot translates over into a zeta of around 0.86, which tells us that we need a phase margin of less than 86% to make sure that we meet all of our design specifications.
Within our transfer function, we still need an integrator. Therefore, we used a PI controller. Shown here is our PI controller function, which we found within Simulink. This is our proportional coefficient and our integral coefficient. That adds the integrator to our transfer function. And we iterated within Simulink until we met our design criteria for our PI controller function.
Simulink model of the system can be seen. Now, through iteration, we found this time series plot as well. We also determined that the specifications of this time series plot was that it had a rise time of 3.59 seconds, a settling time of 16.5 seconds, a percent overshoot of 3.81%, an infinite gain margin giving a steady state error of 0, a 85 degree at 0.517 radians per second phase margin, resulting in a closed loop system that is always stable. And these specifications meet our design criteria. Now you can see a time series plot of this system with a disturbance of a step input at time equals 10 seconds. And what you can see from this graph is that as the disturbance happens, as time goes by, the final value is still achieved, and this simulates the car going up a small hill, receiving some small disturbance, and the controller takes it into account, but still smoothly gets back to the final value of 30 feet per second.
Our analysis of a self-driving car velocity controller. We'd like to thank our professor, Chris Colston for being a great teacher and giving us the knowledge we needed to finish this project.